All right, so that's our schedule. What did we do last time? We are working on solving difference equations, and we went from a zero input to the next simplest input, which is a single impulse. So when we have a system at rest, no initial conditions, and we put in a single impulse, so we let the input f of k equal delta of k. By definition, we call the output of the system, in that case, h of k. So we kind of reserve h of k for this special case of a system at rest and the input was an impulse. So just be writing down h of k, you know those were the circumstances because that notation tells us that. One thing we'd like to be able to know is how to solve for h of k. How do you solve this difference equation under that input of an impulse, system at rest, and the output? How do you solve for h of k? We didn't prove or derive this equation. We kind of reasoned through why this made sense. The initial impulse provides possibly the output right now and also kind of gets the system going. It might impart some initial conditions. Once those initial conditions are established, we know what happens. The system evolves according to linear combination of the characteristic modes, which is what this term is. So we kind of gave this equation and we evaluated it, didn't really derive it. Also talked about how picking off these coefficients is really easy, right? You can figure out what B0 is, what A0 is very easily. But what happens if A0 is 0? Well, you have to modify this and add another impulse in. What happens if A1 is 0? You have to keep kind of tacking in impulses, delta k minus 1, delta k minus 2, until you get to a value of A0 that is non-zero. So we did some of that. Then we basically derived this equation right here, which tells us I can compute the output of my discrete time LTI system for any input as long as I know the impulse response. So this equation we derived, and it assumed linear, it assumed time invariant. To get the math to work out, we had to make those assumptions about the system to derive this equation. So we derived this equation last time, which is a very useful equation. It's called the convolution sum, but we did not actually practice using this or talk about its properties or anything related to that today. What we spent the rest of the lecture talking about last time was solving for the difference equation. So there's always two ways to decompose the total solution. I like to do it this way. The total solution is always a sum of the zero input response plus the zero state response. Those are the two pieces we like to talk about. Often in this class, we're sometimes not real clear. We say, how does compute the output given this input? To be more clear, we should say, assuming no initial conditions, the system's at rest. We should always say that to be very clear. But sometimes we get in the habit of just saying, hey, compute the output for this input, kind of implying the system is at rest, so they're not very clear. And that's why we do convolution all the time, because that's the zero state response. System at rest, nothing going on, and you put something in. So this is what we tend to focus on. However, if there are initial conditions, this component right here, the zero input response, is what we compute. This is the way we'll typically do it in this class, although last time we spent 30 minutes or so talking about what I call the classical approach. If you want to know the forced response of the system, tell me what the input is, I guess what y phi is based on a table or Googling, I plug it into this equation right here to get some equations, and I solve for y phi. So that's kind of the classical approach. That's typically what you do in a diffie class, you make that guess. We're going to go back to this approach today. This is much more general. It works for any input. It doesn't have to be in a table, because as long as you know how to do convolution, this convolution operator works no matter what the input f of k is. We did talk about one special case for computing the forced response. It's really easy, though, and that's when the input is some exponential, some number to the k. I don't think I said this word last time. I probably should have. This input, z to the k, is special because look what comes out, z to the k. Except it's been multiplied by this number that we call h of z. So if z to the k comes in, z to the k comes out, it's just multiplied by a number. That property has a special term, we call that an eigenfunction of the system. If you've anybody taken linear algebra? Couple people taking linear algebra. If you remember eigenvalues or eigenvectors, if you had a matrix, some vectors were special in that when that matrix operated on them, guess what came out? Exactly that vector, except it got multiplied by a scalar lambda. So these were also special kind of vectors that what went in is exactly what came out, except multiplied by a number. Exactly why we have the definition here that we do. This is what it went in. This is exactly what came out, except just multiplied by a number. So exponentials are eigenfunctions of systems. So Because of that, cosines are as well, right? You can write a cosine as a linear combination of exponentials. So when you put in the cosine, what comes out? The cosine. It's just amplitude and phase has been changed. So I'll let some of that sound. All right, so here are the charts we'll be working through today. Work on convolution, and we'll do a whole bunch on convolution, and we'll talk about system properties to wrap things up. All right, so let me just make sure we're talking about. So first, a few properties that might come up as we work through these examples. So we defined last time what this star means. Let me go pop it up again. I should have left it up actually. Lecture summaries all the way to the bottom. So the shorthand that we use for F involved with H is this star right here. And what we mean is write down this sum, right? I'm just going to write that out long form so we're all on the same page. So if I write y of k equals f of k involved with h of k, I really mean write down the sum from m equals minus infinity to infinity, f of m, h of k minus m. So that's what I mean to do. And where people kind of get confused is on this side of the equal sign, the time index is k. Right? I can pick any value for k I want to query y. But on this side of the equation, really the time variable is m. I'm summing over all m. So pick k value, I don't know, k equals 3. K is a constant over here, h of 3 minus m, and I have to do this m operation. So I'm kind of living this other world where I'm doing all the math, and I have to sum over all m for a fixed value of k to get out one value of the signal. And we'll get some practice with that today. But this is a reminder is what we mean by this convolution operator. And what we're going to talk about here are just a few properties. This first one is that convolution is commutative. I can flip the order, and that doesn't change anything. So I can do h1 convolved with h2, or h2 convolved with h1, whichever order you prefer. So that's the commutative property. In this equation, what that means is this is also equal to h convolved with f. Right? I can flip the order. I can do f convolved with h, or I can do h convolved with f. Those are the same thing. If I write down the definition of convolution based on this ordering, the way I always remember it is I like to leave this first one just by itself. So here, f was first, so I wrote down f of m. Here, h is first, so I'm going to write down h of m. And then it's that second one that you flip and shift. So this would be times f of k minus m equals minus infinity to infinity. So you can do it in any order that you want. Let me close that, keep alt tabbing back to it. So that's one property of convolution. We didn't prove it here. I think on my website I have proofs of all these. We're not going to go through the proofs though. It's not too hard. Just write down definitions, do some swaps of sums, define some change of variables, a lot of algebra, nothing too profound. Other property of discrete-time convolution is that it's distributive, meaning if I convolve with a sum, that's the same as convolving and then adding two sums. So far this convolution operator looks just like multiplication, right? Multiplication is commutative. I can do it in any order I want. 2 times 3 is 3 times 2, the same thing. And also multiplication is distributive, right? The distributive property of multiplication, this and this, this and this, the exact same property here, but it's for convolution, obviously. Again, this right here is not a proof, but you can prove it pretty easily just by writing down this and then doing a lot of algebraic manipulation to turn it into this. I've got videos on the website. You can watch that if you like. What else? Guess what else? It also has the property of being associative, meaning I can put parentheses around convolution operators however I want. If I have a convolution of 3 things, I can do this convolution first and then this convolution second, or I can do this convolution first and then this convolution second. Just like multiplication again, right? Multiplication is associative. It doesn't matter how you group your multiplies, do it any way you want when you're done, it's all the same thing. So in many ways, and I think personally, I think that's why we chose a symbol that's kind of similar to multiply, because it's really similar to multiply in terms of properties, although it's obviously a very different operation. So those first ones we use a fair amount. These last couple, not as much. Time shifting tells you what happens if you know the convolution. So let's say I know that H1 convolved with H2 gave me this new signal C. And then I come along and tell you, well, I don't want to compute this convolution. I want you to compute the convolution of a time-shifted H1 and a time-shifted H2. This time-shifting property says that's not all complete rework. All you have to do is take your original answer that you got and shift it a total amount minus m minus n. So whatever these got shifted by, add up those shifts, and then take C and shift it by that amount. Make sense to everybody? So if initially you got out this kind of triangle centered at time 0 maybe, do the H1 convolved with H2, and I say, shift H1 2 to the left, and then shift H2 3 to the right. Well, that's a net of 1 to the right. Well, then your triangle's going to go 1 to the right. That's all you got to do. Time shifting property. Ooh, we talked about this at the beginning of the semester for continuous time convolution. We said convolving with impulses is easy because guess what happens? All you do is take whatever signal you had and you kind of place it at the location of the impulse. And by place it, you have to be careful. The easiest way to think about it is the origin of your original picture gets put at the location of the impulse. If you happen to have a triangle centered up at the origin, it's like taking the triangle and placing it there. But don't make the mistake of just taking the shape wherever it's at and slapping it down. It's really the origin gets moved. Let me draw a little cartoon here. So say we had this signal. Here's K. There's minus 1, 0, 1, 2, 3. Well, let's say I have this signal right here. It's just ones for those 3 values and 0 everywhere else. And let's say I convolve that with an impulse at time 2. So what happens? So let's say I convolve it with this impulse right there at times 2. The result of this convolution means take this and place this 0 right there. I take the time origin here and place it at the location of that impulse. So after I do that, what am I going to have? Here at time 2, that's where this 0 was initially. I'm going to have 0, 0, 1, 1, 1, and then zeros for the rest of time, right? Everybody good with that? So actually where this is centered up now is at 2, 3, 4, 5, 6, 7, right? Well, I drew my origin in the wrong spot, obviously. Let me erase that. 0. Right? The mistake people make sometimes, they look at this and they say, ooh, it's this rectangle, I'm going to take this 3 and put it right there. Yeah, don't do that. It has nothing really to do with the shape. It's this time origin is placed at that location, so it gets shifted to that. So here in pictures is the property, and then mathematically, here's what really happens. You replace this argument by whatever this argument is. That's how I think about it in terms of kind of algebraic substitution. There's a nice width property. We've talked about this before for continuous time. How do you figure out kind of the start and stop boundaries? That's often the thing that you need to do before you kind of work out the convolution. Kind of need to know where you might start and stop. It's just helpful. This has to do with width, the final total width, but it's similar to this property. The width property says that figure out what length each one of these is. The final width of the signal is at most m plus n minus 1. So it gives you a feeling for how many values you're going to need to compute when you're done. So if this is a triangle that has 4 values, and this is a square that has 3 values, when you're done, 4 plus 3 minus 1 is 6. You're going to have 6 values that you need to compute. So those are some properties. Most of these should sound familiar because continuous time convolution was also associative and distributive and commutative. All right, now the thing we'll spend a fair amount of time working on are doing some examples. What we want to be able to do is how do we evaluate this if I give you 2 signals? How do we actually plug into this and do the math? So as usual, we're going to start off with examples that are kind of simple. We're going to start off with signals that maybe only have like 2 non-zero values. And you can almost just kind of evaluate this numerically, point by point by point, to kind of get a feel for the math. But then we're going to make signals that are longer, or you can't do that, so you have to do it for forever. So you have to be able to know how to do it how you used to, with reflecting and shifting things and having all the cases. Sound familiar, everybody? So we'll start simple, and we'll build up in complexity, but this is what we would like to be able to evaluate for any pair of arbitrary signals. So convolution sum example. Here are the signals that we will deal with. K, 0, so at time minus 1, 2, 3, 4. At time minus 1, it's equal to 2. At time minus 2, it's equal to 1. And everywhere else, it's 0. And again, remember the convention, if I only draw these two lines, you just assume everything else is 0. I went ahead and drew some zeros there for you. That's 2, and that's 1. And this is signal F of K. So that's one of the signals we'll deal with. And then the other signal, 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2. We'll call this G of K. And it is 0 almost everywhere except for at time 2. It is equal to 2, and at time 3, it is equal to 1. That's 0 everywhere else times. That's 2, that's 1. So those are the two signals, and guess what we're going to do? We are going to compute F of K convolved with G of K. That's what we would like to do. So as a first step on something like this, so no, yeah, this only has 2 non-zero values. This only has 2 non-zero values. One of the things I usually like to do when you're dealing with what we call finite width signals, that's what I've been calling it, right? This only exists for a very finite period of time. This only exists non-zero for a finite period of time. So you can really easily compute these start and stop points. And the rule is the same as it was previously. You look at where this one starts, minus 2. Where's the first non-zero value over here? 2. So minus 2 plus 2 equals 0. So after I do this convolution, all values below time 0 have to be 0. This is the first chance I get to be non-zero. So after we do this convolution, what should we call it? Let's just call it Z of K. Z of K equals F of K convolved with G of K. So Z of K for K less than 0 has to equal 0. This point right here is the first chance it might be non-zero. So that was kind of like the starting point. What about the stop point? Same type of thing. Figure out where the last value is here at minus 1. Figure out where the last value is here at 3. Add those together, you get 2. So that tells me that Z of K for K greater than 2 has to be equal to 0. So the start and stops really tell me outside of these times where I must be 0. And it kind of lets me hone in on where I might be non-zero. So that's pretty nice. So for all K less than 0, all K greater than, sorry, everybody's looking at me, I'm crazy because I said 0 again, it's 2. Sorry about that. Everybody feel better now? Okay. So if I'm bigger than 2 or if I'm less than 0, that only leaves the points 0, 1, and 2. There's only 3 points that we really have to compute here. So there's only 3 points. Let's just do it kind of the easy way. Let's just kind of plug in a value for K and compute Z of K. And there's only 3 of them. So for K equals 0, K equals 1, K equals 2, let's just plug into this definition right here and just see what the math says it is. There's only 3 values that we need. For the next examples we do, there's actually going to be like an infinite number of values. You can't do that for k equals 0, 1, 2, 3, 4 up to infinity. But for this one, you can, because there's only 3 non-zero values. So let me write down z of k equals f of k convolved with g of k, convolved with g of k, which we know is just shorthand for the sum from m equals minus infinity to infinity, f of m, g, k minus m. All right? So this is what we're trying to compute, and this is the sum that we need to evaluate. We just determined that there's only a few values that we need though, right? One of those is k equals 0. So if I come over here to z of 0, so I've replaced k with 0, I need to replace k over here with 0 as well, right? So that's the infinite sum, m equals minus infinity to infinity, f of m, g of 0 minus m. Okay, so what does this sum say that I need to do? It means I need to take f at time m multiplied by g at time minus m. I need to add up an infinite number of things. However, lucky for us, f is 0 most of the time, right? So when this is 0, 0 times whatever this is 0. So even though it looks like there's an infinite number of things to add up, almost all of them are 0. Let's just do it in our heads. From m equals minus, m equals, I don't know, minus 10, 0. Minus 9, 0. Minus 8, 0. As I come up, though, eventually I get to m equals negative 2. So this is 0 plus a whole bunch of zeros, plus I finally get to when m is minus 2, right? M is minus 2. I get some non-zero thing here. If m is minus 2, minus minus 2 is 2, and I get times g of 2. What's the next term? Well, I'm counting up with m. Minus 3, minus 2, minus 1 is the next term. Plus f of minus 1 times g. 0 minus minus 1 is 0 plus 1, which is 1. All right. Plus, counting up an m. M is minus 3, minus 2, minus 1, 0. Oh, but guess what f is at that time? 0. Plus 0, plus 0, plus 0, plus, right? So I get a ton more zeros. So in that whole infinite summation, there's really only 2 terms in that whole thing I need to add in because they're non-zero. Everybody follow that? So for finite width signals with just a few points, kind of just writing this out is almost the easiest way to do it. All right, let's keep going. We haven't finished though. What is f at times minus 2? F at minus 2 is 1. So that's 1 times, what is g at time 2? G at time 2 is 2, right? 1 times 2 plus f at times minus 1 is 2, plus scroll up and down, sorry. And g at times 1 is 0. So you got a 0 there anyway. I think it's easier though to focus on this term, because that's the one that's, you're just going m equals minus 10, minus 9, minus, just walking through time. And it's very easy to pick off where it starts and stops. This one's a little harder to see because it's a negative, and sometimes for different values of k, it's 2 minus m. So I almost always just focus on this term and letting that kind of turn off and on terms. Although, this one even itself got turned off because that was a 0. So each one of these things I have written down is for a different value of m. So this right here is when n is minus 3, minus 4, minus 5, minus 6, which is why I was getting 0, 0, 0. Okay. Eventually I got to here and m was minus 2, which is why I have minus 2 here and positive 2 here. Yeah, sure. This next term is the m equals minus 1 term. So let me just write that here. So this is m equals minus 2. This term is m equals minus 1. I'm just counting up, minus 3, minus 2, minus 1. This term right here is the m equals 0. This is the m equals 1. I'm just writing down each product of this sum. And n is how we're counting up. All right, so after we multiply that, 1 times 2 is 2 plus 0 equals 2. Very good. Let's do it for another value. I said there's only 3 values, k equals 0, k equals 1, k equals 2. So we're almost done. So k equals 1. To compute z of 1, I come to my definition convolution, and I replace all of the k's by 1. It's horrible looking at when we try that again. Right? Same game. Start n at minus infinity, minus 10, minus 9, minus 8, minus 7, minus... The exact same terms are going to be non-zero, right? Because f was turning things off and on. So I'm going to get 0 plus 0 plus 0 plus... What's the first value for n that I get a non-zero thing? Most likely has to be m equals minus 2. Right? Because this doesn't change. This is always f of m. M is counting up. Minus 3, minus 2. What's a little bit different is here now I have 1 minus minus 2. That's 1 plus 2. That's 3. So now I have g of 3. Right? Plus f of minus 1. M is just counting up. Minus 3, minus 2, minus 1. So the f's never change as we go down this list. G changes though, because now I have 1 minus minus 1 is 1 plus 1 is 2. What about the rest of the terms? They're all 0 again because I go to f0, which is 0, and f1, f2, and f3, and f4. So I have a ton of other zeros here for forever. We go back to our picture. At time minus 2, the signal f is 1. At time 3, the signal g is 1. At time minus 1, the signal f is 2. At time 2, the signal g is 2. I was just coming off the plots now. Want to do faster? So if you add all that up, you get 5. So you kind of get in the pattern. Look, there's a nice little pattern here. I don't know if you noticed this. When I am computing this time, so here was me computing z at 0. These numbers right here always added up to 0. Minus 2 plus 2 is 0. Minus 1 plus 1 is 0. Same thing happened here. I'm computing time 1. 3 plus a negative 2 is 1. 2 plus a negative 1 is 1. You'll always have that pattern because look at the definition here. The definition is m, k minus m. Add those up. M plus k minus m. The m's go away. You're left with k, which is this value over here. So as you're writing this out, it's easy to make mistakes. It's a little tedious. One thing you can always check on, first of all, this first one should always be counting up. Minus 3, minus 2, minus 1, 0. So that one just goes all the way up. And once you've written that down, you almost don't have to think about this one. Just put whatever number is here such that when you add it to this, you get the k that you're on. So if you know you've written down f of minus 2, this has to be 3, because 3 minus 2 is 1. And if you've written down f of minus 1, you know you have to put a 2 here, because 2 minus 1 is 1. And if we had written down the next term, f of 0, guess what I have to put here? I have to put down g of 1. And if I had written down the next term, f of 1, guess what I have to put here? G of 0. And you kind of see they're kind of going in opposite directions. This one's counting up, minus 2, minus 1, 0, 1. This one's counting down, 3, 2, 1, 0. So there's a very nice patterns to this. And hopefully if you write it out kind of organized, you'll kind of see where you messed up. One more value. K equals 2. So I come back, my definition. Replace all the k's with 2. Same game. Guess how many terms there's going to be? I don't even need to think about this now. What has to be here? It has to be g of 4. because 4 minus 2 is 2, plus f of minus 1. So at this point, I'm just thinking in my head, oh, I'm going to list only the times where f exists, and then put whatever g value makes them sum up correctly. This has to be g of 3. Which if you multiply this out, this is 1 times 0 plus 2 times 1 equals 2. And that's it. For all values k less than 0, we know our signal is 0. For all values k bigger than 2, we know our signal is 0. So if this was me on a test, my final answer I would write down would look like this. It would be 0 for k less than 0. Be 0 for k greater than 2. And you could write that down off the bat once you figure out those limits initially. Then all that's left is just filling in a few values here. What were the values? It was 2 at k equals 0, 5 at k equals 1, and 2 at k equals 2. Okay? All right, so this one wasn't too bad because we were lucky enough to be handed signals that only existed for really short periods of time, right? What if f, started at minus 2 and went to time 275? That's a lot of values to compute, right? You could code it up in MATLAB and do it pretty easy, crazy fast. That'd be easy, no problem. You probably would not want to do this for more than, 3 or 4 terms, probably. Get pretty tedious. All right, that basically leads us to our next approach. We call it the reflect, shift, and sum approach, which is exactly what you did in continuous time linear systems. The way we kind of think about that product is there's one signal that sits there and kind of is unchanged. The other one is the original signal that's been reversed, shifted somewhere, and then you multiply that stuff and integrate it up. We're going to do the exact same thing here. We're going to plot our starting signal and leave it alone. We're going to take one of the signals and time reverse it and shift it. Then we're going to multiply them together and add them all up. And then we're going to keep sliding that shifted thing from minus infinity all the way up to time infinity. If we have equations for these signals, then we can actually solve these summations in closed form and give out an equation that's good for all time k. So even if you have a signal that goes for forever, you have an equation that's good for all time k. All right, so this is kind of the algorithm, and we're going to walk through 2 different examples of this. Reflect, shift, and sum approach number 1 and 2. This will probably take us up to the break, I'm guessing. Keep it staying. Reflect. Shift. Sum. Number 1. So here are the signals that we'll work with. X of k is alpha to the k, u of k. And h of k is just a unit step. I'm going to go ahead and tell you that alpha is a real number between 0 and 1, so 0.8, 0.2, something like that. And guess what we're going to compute? We're going to compute y of k, which is the convolution of x with h. What is that convolution? That's our job right now to figure out. From the definition, we know what that means. That means do an infinite sum from m equals minus infinity to infinity, x of m, h of k minus m. That's what I need to evaluate. And being able to write this definition is important, I think, because the key to doing convolution correctly is understanding what this signal looks like and understanding what this signal looks like for different values of k. Being able to know, you have to know what this looks like, you have to know what this looks like, so you can multiply them together. And after you multiply them together, then you have to still sum over that whole time. So let's do that. Let's very carefully sketch this signal and this signal. And that's really the hardest part. If you can do that right, then you're in good shape. But usually people mess up this one right here. I'll kind of give you what I think is the best strategy for that. All right, so first of all, what does x of m look like? I know what x of k is. This is x of k. What does x of m look like? x of m is just x of k with k replaced by m, right? It's just alpha to m u of m. That's all it is. So if I had to plot this signal, it's pretty easy. As a function of m, it's just this decaying discrete time signal that looks like that. It's off at time -1, -2, -3 because of the unit step. So right here at time 0, it's equal to 1. Alpha to the 0 is 1. That is alpha. That's alpha squared. That's alpha cubed. As m gets bigger and bigger and bigger, 1, 2, 3, 4, 5. So that's what x of m looks like. And plotting this one's really the easy one because it looks just like x of k. It's just a different variable you're plotting against. Okay, so people usually don't mess that one up. This is the tricky one, h of k minus m. That's what I need to plot. I mean, here's what I always like to do. I like to do it in steps. So here's the steps that we're going to do. We really want to plot h of k minus m. Here's how I'm going to do it. I'm not going to just try to do this in my head. I'm going to do these little small baby steps. First step is just plot h of m. That's easy. It looks just like h of k. Then what I like to do is I like to do the time reversal. Plot h of minus m. Then I apply the shift. So to get to this, I strongly recommend you really do 3 things. Really make 3 plots total. Plot this, so you see what it looks like. Then plot this, so you can see what it looks like. And then plot this. And during this last step, there's a key thing that people always mess up. I'll give you a trick for the easy way to remember, I think. So let's go ahead and do this. Let's do that sequence. What does h of m look like? Well, h of m is just u of m. All right, it's just a unit step. So that's easy. It's a function of m. It's 0 back here, and it's 1s. Or forever. Up there. Everyone okay with that? It's just a unit step in this example. So we did that one. What about this one? Time reverse it. So I'm just going to take this unit step and flip it the other direction. So here is what h of minus m looks like. That's still m, but now I'm 0 there and 1 in the opposite direction. Everybody okay with that step? It's just a unit step, time reversed. Okay. Now, here's the hard one. I'll tell you the easy way to do this, I think. To go from 2 to 3, I need to take this, I need to shift it by what? K. I need to shift it some amount of K. Here's the easiest way to do that. Find where 0 is on this plot. Where is 0 at? It's right here. Okay. After I shift by K, 0 has to end up at K, because it gets shifted to K. So, this spot right here has to be K. I don't know what K is yet because it's a variable. You haven't told me if K is a big number and I'm above 0, or K is a negative number and I'm below 0. And because of that, notice on both these first pictures, I drew where the time origin was, right? Here is 0, and here's a vertical line for the time origin. And here's 0, and here's a vertical line for the time origin. Here, I cannot draw the time origin because I don't know what K is. I don't know if I should draw it right here, or if I should draw it over here somewhere. Okay? So on this third picture, the easiest way to do it is take 0, redraw this picture just as it is, but label 0 K, because after you've done this shift, 0 moves to K. And don't try to draw a vertical line anywhere because you can't. Okay. So that's really all there is. That's the only trick. It's not that profound, but I think doing these couple steps makes your life easy. This is kind of the algorithm. Just do it that way. After you've done 20 of these, you can kind of do it in your head and just write these down. But I would recommend kind of going through these steps. All right. So we now know what this signal looks like. It looks like that. And we know what this signal looks like. I can now multiply them together for different values of K. So now it's all about different values of K. Where does this thing get shifted to? So let's do that. Let's kind of go through our cases. So be picturing Let me box them. This plot right here is what we're going to multiply this one by. Those are the two things that get multiplied by the sum. So, for k less than 0. Now I've specified a value for k. Now you know exactly where this point is. If k is less than 0, I have a cartoon that kind of looks like, here's the origin, and then I have a signal, like that's one of them, right? K is less than 0 times my decaying thing. I know it's not a continuous time signal, just for the sake of my cartoon, it's a lot easier just to do this for my cartoon. I should really redraw that every time, that would take forever. So what happens when I multiply these together? No overlap, right? This one only exists at negative time, this one only exists at positive time. After I multiply them together, I get 0 for all time. If I add up 0 for all time, what do I get? 0. So this one's the easy case. Y of k equals 0 for all k less than 0. And the only way to know this is I have to be able to accurately sketch these pictures, because you have to multiply them together. So unless you've done these accurately, you're going to be multiplying things that aren't right together. It's going to be a mess. So getting the pictures is essential. All right. Everybody okay with that? What about k greater than or equal to 0? Let me draw just a little cartoon again. One of the signals looks like that. That's the kind of going to the left unit step. The other one always looks the same. That's the same on all of these. One signal always looks the same. You're not shifting it around. Right? There's only one signal that we're shifting around. Will I get any overlap here? Yeah, I get a little overlap from 0 up to k, basically. So there's something to do here now. So let's do that. So y of k, I'll just write out the definition to start. M equals minus infinity to infinity x of m h k minus m. An infinite number of things to add up. But we can start slowly making simplifications. One of them has to do with x of m. It's 0 back here. So at time minus 1, minus 2, minus 3, minus 4, all the way down to minus infinity, x is 0. So this is 0. So these terms are 0. So I claim that I can do this. I'm okay with that? What do? I just really threw out a whole bunch of plus zeros. That didn't matter. Okay. Now what? Very similarly, does this go all the way up to infinity, or do I get to a spot where I start hitting zeros again?
Give it to k.
Yeah, right here. Eventually, I go to 0 here. So at k plus 1, k plus 2, k plus 3, all these values out here, the product is 0 as well. So this sum only goes from 0 up to k, this top edge. That's where that one stops. Okay? So you notice I'm just doing one little thing at a time. You could jump and try to simplify everything, but I like doing one little piece at a time. Lower limit, top limit, etc. All right, what's the next step we might go do? What about this right here? On the interval m equals 0 to k, what is x of m equal to? Alpha to the m, right? It's equal to 1, alpha, alpha squared, alpha cubed, all those values. It's just alpha to the m. Right? For k greater than 0 and m equals 0, 1, 2, 3, 4, up to k, what is this equal to? It's equal to 1. It's these ones right here. Now we're cooking. Hopefully this looks a little familiar. This is a geometric series. It's the sum of some number raised to the counter variable, counter going from 0 up to a number. We have that in our miscellaneous math appendix. So let's go see if we can recall that. So this is equal to, so now this is just a write down from our table. Let me go to it. Miscellaneous math appendix. Here we go. A number raised to the counter starting at 0 up to k. That's almost identical to what we have written down right here.
Would it be alright to just like copy and paste that onto a cheat sheet, like do it
You
handwriting?
get to take all these tables, you get to bring to the exam. Yep. So you don't even have to copy, you can just print it out. Yep. And so what does our table say to do? This is equal to r to the k plus 1. I'll do this, write it down here. Oh man, I can't tap and save my life right now. So the sum n equals 0 to k. R to the m equals r to the k plus 1 minus 1 over r minus 1. Okay, so if we apply that here, we're going to get alpha to the k plus 1 minus 1 over alpha minus 1. Let's think about that. Let me simplify just a little bit. If I multiply top and bottom by minus 1, it just changes the order of the subtraction, which I kind of like this form just a little bit better. It's identical, but I like it better. So I claim that is the output y of k. So as k gets very, very large, alpha to the k plus 1 goes to 0. So in the limit, as k goes to infinity, y of k goes to 1 over 1 minus alpha. So what does this signal look like? What about at time 0? Times 0, I get alpha, 1 minus, I get 1 times 0. So what does y of k look like? It starts off at 1. And then depending on the value of alpha, well, we know alpha was a real value number between 0 and 1. Say it's 0.2, just as an example. 1 minus 0.2 is 0.8. 1 over 0.8 is a bigger number bigger than 1. So this is kind of like asymptotically approaching some value, 1 over 1 minus alpha. As k gets big. So it's kind of this ramping up signal like that. Okay. So let's just regroup and re-highlight. So to me, a few key steps. 1, writing down the definition, which is just a write down. It's just straight off your crib sheet. That's not bad. But then to work the problem, you really need to know what this signal looks like. So definitely plot it. You need to know what this signal looks like. When you plot that one, take these easy steps. Plot h of m, then reverse it, and most importantly, when you shift it, the origin goes to k. That sounds backwards to you, you're right. Well, usually we do like k minus 2, that's to the right by 2, and k plus 2 is to the left by 2. We've already time shifted, so now it's backwards. Now a shift by k moves you to k, whereas it used to move you to minus k. Right? So just remember the rule though, the origin goes to k. And when you draw this, you cannot draw a time origin because you don't know what k is. So don't even try to draw one. Draw it without a vertical bar. And then your cases come from you thinking about, as I'm multiplying these signals together, when do different things happen? First thing that happens is nothing. There's 0, still 0, still 0, still 0, still 0, still. Oh, got some overlap finally. That's your new case. And as we keep sliding, nothing new happens. So there isn't any additional cases on this one. On the next example that will work, there are some more cases and we'll have to deal with those. Reflect, shift, and sum approach number 2. So reflect, shift, sum, 2. Here are the signals that we'll work with. X of k, I tell you, looks like this. It's just equal to 1. At time 0, 1, 2, 3, 4, and 0 otherwise. That's x of k. And then h of k is equal to alpha to k, but only for 0 less or equal to k less or equal to 6, and 0 else. Alpha is the same type of parameter as before. It's real, but here I'm telling you that alpha is actually bigger than 1. So it's still real, but this is a number bigger than 1. So as k is getting bigger, this thing's getting bigger, right? 1.2 squared, cubed, before. So what does this signal look like? That's part of what we need to plot. Guess what I'm asking you to compute? I'm asking you to compute y of k equals x of k involved with h of k. That's what we need to compute, the convolution of these two signals. That should be surprising. That's what we're talking about today. Which means the sum n equals minus infinity to infinity x of m h of k minus m. So to evaluate this convolution, I need to know what x of m looks like. I need to know what h of k minus m looks like. So let's just start making our plots. X of m looks identical to x of k, except it's plotted versus m, whereas that one's plotted versus k. So it looks just like what we plotted above. That one's always the easy one. What about h of k minus m? So let's go through the steps. First, let's just plot h of m. It's 0 everywhere except from times 0 to times 6. So it's a function of m. That's minus 1, 0, 1, 2, 3, 4, 5, 6, 7. Alpha is bigger than 1, so we said this one's kind of blowing up with time. At time 0, alpha of 0 is still 1, so it still starts at 1. But then as time goes on, it's getting bigger and bigger and bigger and bigger and bigger. That's 0 there and 0 everywhere else. Everybody okay with that? For h of m, it's just this equation. That's alpha to the m. But I'm using m instead of k, plotted versus m. That's always the easy one. And there's 2 more plots to make. We need to time reverse this. And after we've time reversed it, then we'll shift it. So let's go ahead and do the time reversal. What does h of minus m look like? Exactly like this, except it's been flipped in time. So now it does this. That's minus 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. This is 0. It's 1. Minus 1, minus 2, minus 3. Minus 4, minus 5, minus 6. All right? Everyone okay with that stuff? It's just this flipped about the time origin. This still isn't the signal I want, though. I want h of k minus m. So here's the hard part, but it shouldn't be that hard because I told you the easy trick. I now take this signal and what do? I shift it k. So the easiest thing to keep track of is 0 goes to k. So you're going to redraw this exactly how it's drawn, except get rid of the time origin, and this spot is now k. So if I could, that'd be a clever thing to do, just erase that vertical line, and then erase these numbers here and replace the 0 with k. That's all you have to do. So I'm going to just draw it right below. Still versus m. So I have that one. So that should look exactly like that above. But what do? We replace 0 with k. So that's k right there. If that's k, that means at this point it's k minus 1, k minus 2, k minus 3, k minus 4, k minus 5, k minus 6. And then it's 0 everywhere else. So it's 0 there, 0 there. Right? So it looks just like this, except now it's at this kind of arbitrarily shifted spot on the time origin. You tell me where k is, I'll tell you exactly where that block of stuff is. All right, so what do we need to multiply? We need to multiply x of m times h of k minus m. These are the two things. These two pictures are the two pictures we need to multiply for different values of k. What's the first easy case? So again, I like to picture this, start at k minus infinity. It's as negative as it can. It's starting to slide up, slide up, slide up, slide up. Initially, is there any overlap? No, it's just zeros times these zeros, nothing's going on. But eventually, this edge gets to, over here somewhere. So for some values of k, yeah, there's just no overlap at all. In terms of cartoon, it looks like times, right? There's no overlap. Here's the time version. They don't overlap at all. The question is, what values of k is there no overlap? K what? This edge right here is k. That edge right there is 0. K less than 0. Yep. If this edge is below that edge, when they multiply, you get all the zeros out. So when k is less than 0, y of k equals 0. That one's not too bad. What about the next case? And again, I kind of like to draw my little cartoons. This continues to slide. It's now not less than 0, it's bigger than 0. So now my next little cartoon looks something like this. Times that still, right? This front edge has slid past times 0. That's k. But it hasn't slid so far that it gets past this front edge. It's kind of just sitting. Actually, let me just draw my cartoon with them on top of each other, because that's what's important, really. So here's my next cartoon, right? So I like to almost shade in this overlap. Here's where they overlap in time, right? K has gotten bigger than 0, but it's less than this front edge. So remember where these edges are. That's at 0, that's at 4, that's at k. So really the picture tells you the bounds for k less than or equal to 4, greater than or equal to 0. This edge is either right here, or here, or here, or here, or here. So 0, 1, 2, 3, or 4. We're going to get 5 points as we do this math. Yeah, what's going to happen eventually, and you'll see it, once this goes past here, we're going to have different terms of the sum because the overlap will be limited by this front edge. So how to determine the cases is the toughest part. And the cases change anytime basically like an edge crosses another edge, because then the number of terms change, or if an equation changes. Like if you have this is an easy one because there's only one equation. Sometimes you have signals that are two different equations and different parts of the equation start overlapping differently. That's when things will change as well. But for us, usually the best way to think about it is things are going to change anytime an edge crosses some other edge. As we do this example, I think you'll see what happens. So let's write this out. Y of k equals the sum m equals minus infinity to infinity x of m h k minus m. That's just the definition. Now what we're going to do is we're going to simplify this for this picture right here. And the overlap is what tells us how to change these limits. Down here, I get zeros because there's no overlap. Up here, I get zeros because there's no overlap. So right away, I know that my limit has to go from m equals 0 to k. That's the only place of the overlap. Outside of there, here I have zeros due to this signal. Here I have zeros due to that signal. It's only here where there's overlap that you get terms that are possibly non-zero. So that's why my limits now are 0 to k. On that interval of 0 to k, what is x of m? It is 1. On this interval, what is h of k minus m? We didn't give an equation for it. This was alpha to the m. This is alpha minus m. This is alpha k minus m. We actually have an equation for that. For each one of these pictures, there's actually an equation. All right? This is m. M gets replaced by minus m, shifted by k. So this is actually alpha to k minus m. always happens. Once you've got the limit set, these limits then let you write down equations for those intervals. Before, from minus infinity to infinity, I can't write down a value for x because x changes as a function of time. Once we limit to this time region, though, it only has the value 1. I replaced it. Same thing here. This is a function of time. I can't just replace it with the equation for all time because as a function of time, it's different. But guess what? Once I've limited it between here and here, it is just this equation. So that's a key thing to do. All right, let's just make that look a little nicer. M equals 0 to k, alpha to k minus n. Just got rid of the 1. Now we just get to do a little algebra. M equals 0 to k. Alpha. You okay with that? All right. Alpha to the k, that's a fixed constant. I'm looping on m right here, right? Hold on. There's an easier way to do this. We could keep going this way and factor that out. Let me do a slightly different, easier way. There's 2 ways to do it. Each one gives you the exact same answer. We could do it the way I was doing it, or we can do a slight change of variable here. Sometimes when you have a weird shift, what's nice to do is this. Let's replace k minus m with r. R equals k minus m. Because I don't like this weird. I want to have alpha to the r. I love alpha to the r. That's the easy thing that's in my appendix, right? So let's force it to be that. If r is k minus m, we need to get rid of all the m's and replace it with quantities in r. So when m is 0, r is k. M is 0, r is k, right? Replace m with 0 to get r is k. When m was k, what do we get? R is 0. So I'm going from limits with m counters to limits with r counters, just to make it look a little nicer. So this is r equals k to 0, alpha to the r. Right? That became alpha to the r. When I was k, now I'm 0. When I was 0, now I'm k. But guess what? This sum is still the same thing. It still means the same thing. Add up from r equals 0 up to r equals k. R equals 0 to k, alpha to r. And this is what we were just doing a minute ago, right? What do? You write down the factor, and you raise it to this number plus 1, which is from the table, right? So k plus 1, so minus 1, and then you do 1 minus alpha, or alpha minus 1 on the denominator. So for this particular period of time, this is the equation that we get. But we're not done. Guess what's going to happen now? This is kind of like a wide thing, and this is a narrow thing. So the first thing that's going to happen is this front edge is going to go past that front edge. Let's do that case. This one stays the same, and this is the wide signal. Eventually, that happens, right? K gets above 4, but k minus 6 hasn't gotten past 0. So again, being able to sketch these cartoons and label these points is important. So, and this picture now tells me the values for k. This is for k greater than 4, and k minus 6 still less than or equal to 0. Well, k greater than 4 really means k greater than or equal to 5, because they're integers. If you're bigger than 4 and you can't be 4, you have to be 5 or 6, right? And then this one tells me k less than or equal to 6. So this next case is actually a small case. We're only going to get 2 time periods out of it. But it's good practice on being able to establish your limits. Where's the overlap? The overlap is from 0 to 4 now. So when we write this out, y of k equals the sum, m equals minus infinity to infinity, x of m, h of k minus m. That picture tells me the limits. The overlap is only the region m equals 0 to 4 now. Of what? 1 alpha to the k minus m. Same type of thing that we did just a minute ago. I'll solve this one the other way. This is sum m equals 0 to 4 alpha to the k alpha to the minus m. All right? Product, you add the exponents. Alpha to the k is a constant, so I'll bring it outside. Alpha to the minus m. This one's tricky. Ooh, watch this. Do this one a lot too. All right? Alpha to the minus 1 to the m, you multiply, so minus 1 times m, I haven't changed anything. Why, but I like this one better. I always like to see a number raised to the counter. My counter's n, so I like seeing a number raised to m. So I make it look like that. So you can almost think of this as now being like, you know, beta or something. Beta to the m, or r to the m, if you wanted to. Well, let's do it. So alpha to the k. This one's interesting. This goes from 0 up to 4. What's the rule? You take whatever this is, and you add 1 to it, right? So alpha to the k times, so here's what I'm going to write in my closed form math appendix stuff from my geometric series. Yeah, it's whatever number you see, you write it down plus 1, and then you subtract off 1. All right, so for us, it's to the 4. So it's alpha to the minus 1 to the 5 minus 1 over alpha to the minus 1 minus 1. It's kind of ugly. This is not a pretty answer, but it's still a signal. It's a function of k. And the values of k this is valid for are k's equal 5 and 6. We getting there? There's one more, or 2 more cases. Let's draw the cartoons for them. K is continuing to increase. Eventually this is going to slide up to here. So our next little cartoon looks like, here's the one I've been drawing all along. Here's the one I've been drawing all along. And now, we got this going on, right? It's slid so far past, the front edge is well past here, the back edge is inside. Where do I overlap now? Just here. Remember, all your labels, that's 4, that's 0, that's k minus 6. So can you guess what you're going to sum from when you do the sum now? What's the lower limit going to be? K minus 6 up to 4. So we'll just kind of jump to the chase. So I'm just going to write down m equals k minus 6 to 4. On this time interval, we have equations for all those things. One is 1, one is alpha to the k minus m. So it's alpha to the k minus m times 1. So if you notice, the thing that's inside keeps being the same. It's just these limits are changing. That's really the hard part, figure out what the limits are supposed to be. All right. This one's a little tricky because I have things in my table, m equals a number to a number, right? And that number is usually 0 down here. Well, there's another one we have in our table down. Look at this one right here. This is for an arbitrary starting number to an arbitrary stopping number. It's just this equation right here. Let me just write that down. M equals m. So if I had a sum that started at an arbitrary number capital M and went to an arbitrary number capital N of r counter, that is equal to r to n plus 1 minus r to m over r minus 1. That's exactly what we have right here. After I do just a little bit of work. That's alpha to the k, factor that one out again. That's k minus 6, 4. Alpha negative 1 to the m. The sum of some number raised to the counter variable starting at some number, going to some number. That's exactly what I have right here. So I can just write that down. It's alpha to the k. And then when I do alpha to the negative 1 I need to raise this one to the top limit plus 1, so that'd be 4 plus 1, then subtract off the bottom limit itself. The bottom limit itself is k minus 6. There we go. We can spend a lot of time simplifying this to make it look nice, but I think just being able to evaluate from the table is the most important part. Okay with that? What's the last? And again, I'm really focusing on this is the key part. We can do algebra all day long and putter through that, but knowing how to sketch that cartoon is really the most important part. What's the last case? What's the last cartoon? K minus 6 what? Greater than 4. Once I've slid past this edge, there's no more overlap again. So I'll go ahead and draw it. So this one has stayed the same the whole time. That's 4, and now we've slid past. That's k minus 6. So k minus 6 greater than 4 is k greater than 10. So here we get y, k equals 0. I think I have both these on my YouTube channel. I work through all the algebra and intricate details. You can watch it if you want. But like I said, I think the most important part is slowly sketch these different cases. And really what matters is these different boundaries. The different boundaries control the limits. And with different limits, you have different answers. So that's the most important thing to understand. All right, let's press on. Two more examples, and we'll talk about properties. Just maybe a touch short on time, so maybe we'll get there. So this next example, we're going to talk about solving for the zero state response, which typically means convolution, right? But instead of doing convolution the way we were talking about, where you actually sketch it all out and kind of evaluate it yourself, we're going to use tables. So make sure you guys know what the table is for some of these common convolution pairs. So analytic approach. Here's your system. It is described as y, k plus 2, minus 0.6 y, k plus 1, minus 0.16 y, of k equals 5f. Should look familiar. This is one from your textbook that we worked a while ago. And for this example we worked a while ago, we actually found the impulse response. If you weren't given the impulse response, you might need to go ahead and compute that first. That's a whole other problem. But we already computed the impulse response for this system. We found that h of k was equal to minus 0.2 to the k plus 4 times 0.8 to the k u. Okay, so that's something we figured out previously. So here's the impulse response of the system. Here's the input. What you're asked to find is the zero state response. We call it y. Okay, this is the output of the system when the system is at rest and you put some signal in, zero state response. We know what that means. That means it's given by the convolution of the input with the impulse response. So what we need to do is we need to convolve for the negative k u of k with that. That's the convolution that we need to do, right? One thing that we can go ahead and do is we know that convolution is distributive. So let's go ahead and distribute that convolution out. So that would be convolved with minus 0.2 k u of k plus 4 to the negative k u of k convolved with 4 0.8 k u of k. So that was the distributive property of convolution, right? So if I was working this problem from scratch, there's really two convolutions to do here. I'll call it 1 and 2. And unless directed otherwise, you would probably be inclined to go ahead and do what we just did, right? Call this the first signal, call this the second, sketch this one, do the time revert, right? A lot of different cases, a lot of different math. But we should be able to do that. What we're going to do is I'm going to show you this convolution table that we can just basically look up common convolutions like this and just write down the answer if it's something that's already in our table. Before I do that though, let me work on this just a little bit. What does this look like? This looks like that 4 to the minus k is really 4 to the minus 1 to the k, right? 4 to the minus 1 is 0.25. So this is really just 0.25 to the k, correct? So we just rewrite it like that, just so it looks. You'll see when we go to the table, it'll be in the table form a little bit more clearly that way. So there's 1 plus. Same thing's going to happen here, and this constant right here is 4. I can just bring out in front of the whole convolution, right? Convolution is just a summation, bring the 4 out front. So this is really 4, 0.25 to the k, u of k, involved with 0.8 to the k. Okay. There's the second one. So the table I want to show you is table 9.1 from your textbook. Rotate this. There we go. And if you look right, so here is signal 1, here's signal 2. This is the convolution of those signals. So if you convolve an impulse with f, you get f shifted to the location of the impulse. If you convolve gamma of the k, u of k with u of k, you get this as the result of convolution. So lots of different cases here. What we have in our case is gamma of the k, u of k, convolved with some other gamma of the k, u of k. The case that we're in is this one right here, case 4. So if we're convolving a signal of this form with a signal of this form, here is the result of that convolution. You just write it down. Okay. So if we do that, equation 1, if I want to call gamma 1 0.25 and gamma 2 minus 0.2, from our table, we're told that gamma 1 to the k, u of k, convolved with gamma 2 to the k, u of k, is equal to gamma 1 to the k plus 1 minus gamma 2 to the k plus 1 over gamma 1 minus gamma 2. Okay. Obviously, gamma 1 not equal to gamma 2, otherwise you run into problems right here in the denominator, right? But we don't have that. 1 is 0.25, 1 is a negative 0.2. So, if I use that here, what do I get for the convolution? I get 0.25 to the k plus 1 minus negative 0.2 to the k plus 1 over 0.25 minus negative 0.2. All that times u. Okay. So that is the result of performing this convolution. You can do the exact same thing for this one, right? It'll be practically identical, except everywhere you have a minus 0.2, you're going to have a plus 0.8, right? And then there's also going to be a 4 out front, just because of that scale factor 4, which goes along with everything. So you could definitely do this for 2, same approach basically, and then just add up both these to get the final answer. So nothing profound here, just wanted to make sure you knew that there was a table. Sometimes on exams I say use the table to find the convolution. You're expected to be able to look at the table and figure out the right pair, just write it down. Other times I say using the reflect, shift, and sum approach, sketch, I make you do it that way. So just make sure you know how to do it both ways. One more example. We're going to kind of pull all of this together. We've been talking about how do you solve a difference equation for y of k that we call the total response. It could be the zero input response and the zero state response. There's really these two pieces. So we're going to kind of walk through an example, the pieces of which we've worked on all these different examples. I'm going to kind of tie it all together here in this one kind of list for you. total response via, basically we did an example where we found the total response using the classical approach. We found the y phi, we found the yn, we tied it all together and got the final answer. Same thing here, except we worked all the pieces. We don't need to go into the details of this kind of reference and things. So here's the system. Y of k plus 2 minus 0.16 plus 1 that we've looked at many a time. And here are the initial conditions. And we have an input. So this is the full-blown everything. And I want to know y of k. What is the total response? We know the total response, the way we're going to work it going forward, is the zero input response plus zero state response. The zero state response we can get by doing convolution, right? That's what we've been talking all day, how you can get the zero state response. And then this one is the, the characteristic modes. So let's just kind of walk through all the steps you would have to do to solve this from scratch if you had not worked on this problem before. First of all, if you go back to difference equation number 1, which is an example that we worked in this class, you could solve for y0 of k, the zero input response. And we did that, and we got this as an answer. That was the answer that we got. So that gets you this part right here, the zero input response. How do I do the zero state? I need to know h of k. Well, thankfully, we already worked that example. We did an example a while ago called closed form solution for h of k. That was what we started off last lecture with, right? And we solved and figured out that h of k equals negative 0.2 k plus 4, 0.8 k u of k. Then you need to take that impulse response and you need to convolve it with this, f of k. That's what we just did in the last example. So in the analytic approach, that's exactly what we did. And we figured out that y, we'll call it the zero state response, y of k, I keep saying y, I keep meaning f of k convolved with h of k equals, there's this big old term here that I didn't even bother. It's from this though, right? After you fill this one in and fill this one in, then add them all up together, you get this big old thing for the zero state response. So that's where that comes from. And now you can tie these things together, right? The zero state response plus the zero input response. And then you would need to use these initial conditions to tie together some of these. So if you're asked to solve for y of k, and there are both initial conditions and a non-zero input, it's a lot of work. You have to kind of go through this whole sequence of getting the zero input response, finding h of k, using h of k, doing convolution, then tying all these pieces together. It's a lot of work, but we're doing pieces of them. And really this example is here just to show you kind of how all these pieces fit together and getting the final full answer without us actually going back and spending 10 pages of writing doing another one. All right, a few charts on system properties. So we are going to look at the impulse response and see what that can tell us about characteristics of the system. So for example, first property is what we call a memoryless LTI system. If you are a memoryless LTI system, the output only depends on the current input. So what we're going to do is we're going to write down the output in terms of the convolution, because that's how we know the output is related to the input. And if you write it out, this is kind of the pattern that you see, and this is the pattern we've been seeing today, right? At some time k, it's really equal to this infinite sum of terms. That's what we were doing today. That's what we did in your quiz, right? These numbers always add up to k. And in general, there's an infinite number of things to add up. Well, if this output at time k can only depend on the current input, here is the current input, right? Time k is what's happening right now. So that means I can't depend on this term, or this term, or this term, or this term, if I'm going to be memoryless. So what that means is if I'm memoryless, my impulse response is pretty simple. It can only be a function of what's happening right now, which means all of these terms have to be 0, which means my impulse response has to be 0 almost everywhere for these to go away. So that means that I'm a memoryless system if and only if my impulse response is a scaled delta function. So if I ever give you an impulse response and it's something other than delta of k with a constant out front, then it has memory. Right? If it's shifted over at all, if it's shifted before, if there's more than one non-zero value, then the output is a function of something other than just the current input, and then you have a system with memory. So systems that are memoryless are very easy to identify, and their impulse response is really boring. It's just an impulse that's been scaled up and down. And if it's anything other than that, it's a system with memory. So most of the things we deal with have memory. It's only kind of this trivial system that does not. All right, what about another important definition? Causal systems. A causal system is one that whose output only depends on current inputs and past inputs. It can't depend on future inputs, because that'd just be weird. How can what comes out of my system right now depend on something in the future? That's impossible, right? So again, if we write out the mathematical equation for the output of our system at time k, here's the string of math that we see. Time k is time right now. So here's my input right now. Here is my input 1 time sample ago, 2 time samples ago. But this is my sample 1 time in the future, 2 samples in the future. Okay? So if y of k cannot be a function of x of k plus 2 or x of k plus 1 or x of k plus 3, I better have a 0 for time minus 1 of my impulse response to make this go away. And this better be 0 to make that go away. Same thing all the way back. So h at time minus 1, minus 2, minus 3, minus 4, they have to be 0, otherwise I'm going to be a function of a future input. And that leads us to our definition of a causal system. I'm a causal system only if my impulse response is 0 for k less than 0. So the same definition you had before, right? If you plot the impulse response and it has non-zero values below time 0, you say non-causal. It started responding before anything even came in. Can't happen. These are probably our 2 most important ones: memoryless, causal, these stability ones. Some of the ones we get to at the end we don't use as much. There are a variety of types of stability that we'll talk about. We'll talk about, here, bibostable, bounded input, bounded output stable. Basically, that means if I put in a bounded input, something that's well behaved, my output is well behaved. So reasonable inputs result in reasonable outputs. Mathematically, how do we say that? Here's how we say it mathematically. We say that if my input's magnitude is less than some number, which is a finite number for all time, so I can find this number that kind of caps my input. If this is true, and that results in an output that is also capped by some number, that's what we mean by bounded input, bounded output stable. So mathematically what we write is this. We say that the input being bounded, x of k being less than some number, which is less than infinity, implies that the output is also. So bibostable means this and true. The input being bounded tells us that the output is bounded. That's what a bibostable system is. What do we do on these first 2 examples? We wrote down what we meant in words by the property. Hey, it only depends on the current input, or it only depends on the current or the past inputs. And then we came up with a criteria for h, that we could just look at h and tell what was going on. we're going to do the exact same thing here. If this is what I mean by bounded inputs resulting in a bounded output, let's kind of plug this into the equation and see what this must mean for H. What's a property for H that we can find? In doing that, we're going to use two properties. This one right here, does this look familiar to anybody? The magnitude of a sum is less than or equal to a sum of magnitudes. We call that the triangle inequality. So it's kind of easy to see that it should make sense, although we're not going to prove it. For instance, if A is 2 and B is minus 2, their sum is 0, and 0 is definitely less than the magnitude of 2 plus the magnitude of minus 2, which is 4. Okay. So anytime you take the magnitude of a sum, it's less than a sum of magnitudes. It always gets bigger. That's what they call the triangle inequality. And then this one, which should just be kind of obvious, right? The magnitude of a product is a product of magnitudes. Okay. 2 times the negative 4 is negative 8. Magnitude of that is 8. Magnitude of 2 is 2. Magnitude of negative 4 is 4. 2 times 4 is 8. So yeah, the magnitude of a product is a product of magnitudes. What we're going to do is we're going to try to find some criteria on the impulse response. So hopefully this makes sense to everybody. The output is equal to the convolution of the input with H. And what did I do? I just took the magnitude of both sides of that equality. Totally legit thing to do. I did the same thing to both sides of the equation. What is convolution? It's just this big old sum, just like it has been all day long. So the magnitude of the output is the magnitude of this sum. Okay? Here we go. From here to here, what did I do? I used that triangle inequality, right? The magnitude of a sum is less than or equal to a sum of magnitudes. That's this property right here. The magnitude of a sum is less than or equal to a sum of magnitudes. I took the sum from the outside and moved it inside. Because look, I have the magnitude of each piece now, all added up. So this was just the triangle inequality right here. From here to here, what did I use? The other fact. I have a magnitude of a product that's equal to a product of magnitudes. The magnitude of this times the magnitude of this. Nothing wrong with that. Then what did I do? From here to here, I made it bigger by assuming a bounded input. We're going to assume we have a bounded input, which means this is capped by mx. So if I replace this with its max possible value for all time, this has to get bigger, right? I got way bigger. So it's interesting. So this first part was just the definition of the magnitude of the output, triangle inequality, some basic math. Here is where I've assumed a bounded input. It got even bigger. I assumed a bounded input. I want to show that that results in a bounded output. I sure would be nice if the magnitude of my output was less than some number for all time. That would mean it's bounded. I can find this kind of max value. That'll be true in a certain case. This is just a number, so I like that. It's almost like I'm less or equal to this number times this number. If this is just a number, I don't know, 45 or whatever it is, I've got a number times a number, and then yeah, my magnitude is bounded by a number. That's exactly what I want. So here's the criteria. I need this to be a finite number. I need the sum of the absolute value of my impulse response itself to be a finite thing. As long as this is a finite thing, I have the product of two finite things, and I have a bounded output. So that's our criteria. You have a bibostable system only if you can sum up the impulse response and get a number less than infinity. I said it wrong. Only if you can sum up the magnitude or absolute value of the impulse response and get a number less than infinity. So that's the criteria. So if I hand you h of k, and you say, oh, I'm going to take the magnitude and add up all those values, and you get 27, you say, yep, this is definitely a bibostable system, because its impulse response is absolutely summable. That's what we call that. Absolutely summable. I can take the absolute value of everything, add it all up, and it doesn't diverge or blow up. I just get this finite. That's one type of stability we discuss often. Bounded input, bounded output, bibostable. There's other ones, though, that have to do with the characteristic modes. When we talk about the characteristic modes, their locations control another type of stability. Whether it's asymptotically stable, meaning the zero characteristic modes die out over time, or if it's unstable, meaning they kind of blow up with time, which is not good, or if they're marginally stable, meaning they just kind of oscillate for forever. They're not getting bigger, they're not getting smaller, they just sit there and oscillate. So those are really 3 other types of stability that we could classify as well. So bounded input, bounded output is one type, and then another type that we discuss are these types of stability: asymptotic, unstable, and marginal, which all have to do with characteristic group locations. I never go over that one, so we never do it. A few more interesting facts. We've been spending a lot of time talking about impulse response. Systems at rest, I put an impulse in, what comes out is what we call H of K. Sometimes it's useful to define what we call the step response. Its definition is almost identical. My system's at rest doing nothing, but I put in a signal. Guess what signal I put in? A step, a unit step. Right? What comes out is what we call the step response. Just like when we put in an impulse, what comes out is what we call the impulse response. So this is just the output of the system due to a step being put in to this at-rest LTI system. If you think about it just in terms of input-output convolution, that's the easy thing to do, right? We know how to compute the output for any input. Just convolve the input with the impulse response. So I could easily solve for S of K, the step response, by convolving my impulse response and U of K, no problem. If I write out the definition, this is what the definition would be in terms of convolution. Since we know that the unit step is 0 for half of the time axis, these limits actually simplify though. You only have to go from -infinity up to time k. Okay? It also turns out that there's a nice relationship between S and the delta function, the impulse response. And they're related by this equation. So if I know the step response, I can compute the impulse response from this equation. Similarly, if I know the impulse response, I can compute the step response. They're just related by differencing and summation, as you might think there. What else? All right, just summary now. So we kind of went through that real quick, but I think most of these things you've heard of before: causality, stability, memoryless. Okay? We now have ways, if I hand you an H of K, for you to check whether these properties hold or don't hold. And then towards the end here, just a summary of all the things that we have done in this chapter. So everything in this chapter has been very much based on time domain analysis. If I give you a difference equation, how do you solve it? If you want to solve the whole thing, that's a ton of work. That means 0 state response plus 0 input response. If I ask you to solve it for 0 initial conditions, that's kind of the easier case. That's just one convolution you have to do. There are no initial conditions, you have to worry about that part. If I say solve it for just these initial conditions with no input, that's the other half of the problem. So we can kind of mix and match as we need to make it reasonable. What often plays a role is the characteristic equation, right? Those roots of that characteristic equation. That drives the characteristic modes, which the natural response and the 0 input response are a function of. Today was all about convolution. That's the way that we can compute the output of our system for any input if we know the impulse response, H of K. That's why this is a very important quantity. A lot of books are kind of sloppy. They say, oh, here's your system, here's your input, find the output. And they really mean the system was at rest, find the 0 state response. That's what they mean. But even I get a little lackadaisical on that sometimes. So unless it's otherwise said, they say just find the output, you kind of assume all the initial conditions were 0. Kind of like when we do our plots. I draw all these non-zero things, but sometimes I forget to draw all the zeros out there. Well, if I don't tell you about them, you just kind of assume they're 0. If I give you H of K, not only can you compute the output in the time domain from any input, you can now analyze properties of the systems. You can tell me if it's memoryless or not. That's easy. If it's just an impulse response, scaled up and down, a single one, it has no memory. If it's anything other than that, it has memory. You can tell if it's causal. If it has any values below time k equals 0, it's non-causal, otherwise it's causal. You can tell me a variety of different flavors of stability. If it's absolutely summable impulse response, then it's biostable. If you know things about the characteristic modes, you can tell me whether it's asymptotically unstable or stable. We don't really do invertible here. I used to do that, we don't do that as much. So that is it.